It's 1 over 1 plus.
No.
Yeah, you guys, this isn't working. Actually, this is a derivative of the inverse tangent, but like I was saying before the break, if you can't anti-differentiate something like just like that fast, but you can differentiate it, I think that means it's a prime candidate for the employment of the integration by parts formula. Yes?
Moving from 0 to 1.
Oh, thank you. I forgot. Actually, it should still be up there. Ah, you are absolutely correct. So everybody, I think I only have 2 choices for my assignment for you and DV. I'm going to let you be something, DV be something else. Don't you guys agree that I won't let DV be the inverse tangent of x? Back to the question. I just got to anti-differentiate again. Which is the question? I think my only realistic choice is to allow you to be the inverse tangent of x, and DV be everything else. Now, paying the consequence of my actions, no tricks this time. I really do think the derivative for you is 1 over 1 plus x squared dx. And I do think v is a piece of cake. Yes? Ooh, but it isn't. And I think that's a completely different expression. It'll be a slightly harsh punch, I think. But you guys, think where we're at right now. This is our 5th quiz. And I was just talking to somebody about this. This Friday, in class, there's 6 quizzes. But if this Friday I give you a take-home, that's 7. That means in 3 weeks I got 7 quizzes. That means in 6 weeks that gives us 14 quizzes. Another 2 weeks, maybe a few more on there. I mean, we're looking at about 17 quizzes for the entire summer session, so you got plenty of room to make silly, goofy mistakes, right? Right. And everybody, I think this looks nice. I think the product of my u and v is this mathematical beast. Whoops, hold it, I wrote incorrectly. I meant this mathematical beast. And I'll evaluate from here to here. Minus the integral of my v du, which in this case, look at this, you guys. Isn't this pretty? Nice, quick, easy
U sub.
U sub. And I think that leaves me with a product of x inverse tangent of x. And anti-differentiating, isn't that just simply merely a 1/2 natural log of 1 plus x squared?
You want to make sure that well, no, you changed it from the U sub. I changed the bounds.
You know, you're right.
Yeah.
I just back substitute.
Okay.
And I think I need to evaluate this beast from, well, here to here. But I think that merely gives me, I have no idea what it gives me. It says that pi quarters. Minus 1/2 natural log of, is that a 2?
Yep.
Minus 0, oh, plus 0, they're gone. And so I think in the end I'm merely left with a natural log of root 2. Oh, I misspoke, didn't I? I meant pi quarters, minus that.
How'd you get the natural log of root 2?
I just brought the 1/2 of the exponential position.
If you didn't do that, is that if I just left it like pi over 4 minus 1/2 ln of 2?
No, I think maybe yours looks better than mine.
Okay.
In fact, maybe it looks better if I pull out a 1/4.
Is it right either way?
Absolutely. Well,
Okay.
in any of these 4 ways. I have 4 different answers. I think they're all equally nice.
Okay.
You mean the bounds? If you're not going to back substitute, yes. Notice how I cheated. I applied a u sub to my head, but back substitute in terms of x, not u, which allowed me to put back in my original bounds of integration. Yes.
So, when I was doing this problem, I did everything correct except the last line. So I did the integration by parts correct. I did the u sub correct, and then because thought I was running out of time, I just plugged in numbers wrong somehow.
Oh, gotcha. I think the most important part is up to here. I think the numerical evaluation again is not quite as important. If you want to know how I emphasize my grading on a question like this. Anybody else?
He's a
I
genius.
changed it
He
back
can do
only because
stuff
I
like
back
that.
substitute in terms of x. And if you don't back substitute, that's fine. Keep in terms of u. You're going to have the integral of 1 over u with 1/2 out front, ranging from 1 to 2. And then keep them as such, and you'll get exactly the same answer I do. It works beautifully. Did you really? Can I do it your way then real quick? Let's do it your way. Because I think you're going to end up with this. Committee u sub. Phi allow u to be 1 plus x squared. Certainly du is going to be this. So look at this x dx. I think another name for it is just this. So far, so good. Oh, by the way, everything else downstairs, I guess it's pretty direct. I guess it's just a u. And I think if x is equal to 0, then the corresponding value for u is going to be positive 1. But if x is equal to 1, plugging 1 in for x, I think the corresponding value for u is here. But that merely leaves me with pi quarters minus 1/2 times the natural log of u evaluated from 1 to 2. And I know I'm cheating, you guys. I should have absolute value bars in here in general. It's just that over this particular interval, I know it means positive. And I think that's going to give me my pi quarters minus my 1/2 times, let's evaluate. I've got the natural log of 2 minus the natural log of 1, but you know what? The natural log of 1 is clean. And I think I'm merely left with the pi quarters minus 1/2 natural log of 2. You guys help me. I don't remember. Is that the answer I got?
Yep.
So barring any numerical errors along the way, I think that that's the same. Yes, sir.
Why don't you use 3 pi over 4? Does that get eliminated somehow? Because
Ooh.
inverse tangent of 1.
Whoa, what a good question. I do think 3 pi quarters over 4 is
Outside
negative,
of
tangents related, but it's negative 1. Because in the second quadrant. Because I think when it comes to 3 pi quarters, check this out. X-axis, y-axis, unit circle. Here's pi. Here's a point in unit circle associated with pi halves, or 2 pi quarters. So I think the point in unit circle associated with 3 pi quarters is going to have coordinates negative root 2 over 2.
Oh, no, not 3 pi fourth. 5 pi over 4th.
Gotcha. Well, here's a point in unit circle associated with pi quarters. It is true that its coordinates give you a ratio of y to x, which is positive 1. I'll buy that. No, do this. X-axis, y-axis. Let's graph this beast. You guys, I know I'm being a little sloppy, but let's just talk about this function real quick, because I want to generate its inverse. So you ready?
So you have to eliminate everything to the left of negative pi fourths and to the right of pi fourths.
Thank you. I think I can't discuss the inverse of this function. It doesn't exist. I think this graph miserably violates the horizontal line test. That being the case, this cannot be a one-to-one function. Therefore, it cannot have an inverse. However, if I restrict the domain of this tangent function from this vertical asymptote to this one, in other words, putting on a special pair of mathematical glasses, I do not see the graph of the tangent function outside those two vertical asymptotes. Notice how number 1, this is the one-to-one portion of the graph of the tangent function. Number 2 spans all y values that are all values in the real number system. And so this is what I'm going to use as a tangent function with the restricted domain to construct this inverse. Now I'll reflect this beast through the line y equals x and check out what I create. I'm now going to create the inverse tangent function's graph. Looks something like this. I'm being a little sloppy. Where I've got horizontal asymptotes here and here. But going back to the original black one, notice I'm dealing with angles between negative pi halves and positive pi halves, not beating this to death. But I think there's only one angle on the unit circle between negative pi halves and positive pi halves whose sign is positive 1, and that would have to be pi quarters. It's It's only because that restricted domain. Even though I gotta agree with you, 5 pi quarters does have the quality, I misspoke, 5 pi, yeah, I'm right, I wrote it wrong. 5 pi quarters, not halves, has a tangent which is positive. It's just not my desired. Anybody else? Okay. Before I get started with my examples, do you guys mind if I jog your memory a little bit? Jogging your memory a little bit. Help me with this.
The sine inverse.
What can you say about this one?
Tangent inverse. Plus C.
That being the case, what do you think you can say about this one? By the way, that's an 8 out of 9. Say it one more time. You're right there. You're right there. The inverse sine of x over a plus c. Why? You let be what? Close. You let x equals x equals. I can't hear you. Better. I like your last answer. He's saying this. Let's commit to a substitution. Let's allow x to be equal to a times the sine of theta and pay the consequence. This is one of my trig substitutions that I started discussing last time. In committing to this, I think I've got the integral of 1 over, I'll slow down. Putting a sine of theta in for x. Underneath the squared symbol, in a radicand's position, doesn't that give me a squared minus a squared sine squared theta? Now pull the 8 out. Those two factors, now pull out a square root symbol. You just get a. But now I got the square root of 1 minus sine squared of theta. But that's the square root of cosine squared of theta. But the square root of cosine squared of theta is, isn't it just simply sine of theta? I'm sorry, did I misspeak?
Yeah.
I did. The square root of 1 minus sine squared of theta is the square root of cosine squared of theta, which is cosine of theta. Oh, shoot. Maybe that's a mistake. Actually, the square root of cosine squared of theta actually is the absolute value of the cosine of theta. However, if I isolated theta here, wouldn't it be the inverse sine of something? And if when I isolate theta, I get that theta is equal to the inverse sine of something, that's an angle between negative pi halves and positive pi halves, an angle in standard position in the fourth or first quadrant, but the cosine of any angle in the fourth or first quadrant is going to be positive. This is what gives me the Math D legal right to suppress absolute values. I still missed something, darn it. Oh, I guess I missed my dx, which has this alternative name. Notice how everything cancels, and I'm merely left with the integral of 1 with respect to theta. And I can anti-differentiate, and I can back substitute. Another name for theta is just the inverse sine of an x over a plus c. So I maintain from now on, if you see the integral involving a 1 over, not 1, but how about an a squared minus x squared, from now on, do you guys think I could just cut to the chase? I just proven to you that this is nothing more than inverse sine of x over a plus c. There's another one I want you to consider before I dive into my examples. Another one to consider is this important one. It just pops up, you guys, enough for me to want to deal with it. Relative to what I discussed last time in class, what do you think the appropriate trigonometric substitution should be? So a times tangent of theta. That being the case, paying the consequence, I think dx is nothing more than a times the secant squared of theta, d theta. You guys relax. I'll finish this one. Committing to my substitution. I think downstairs, a squared plus x squared is a squared plus a squared tangent squared. You tell me if I'm skipping too much. That's a squared times a quantity. 1 plus tangent squared. But 1 plus tangent squared of theta is the same thing as.
Secant squared.
I agree. Oh shoot, I missed something. I forgot my dx. I'll put it in. I think another name for dx is here. Yes or no? Just like in my last example, are you happy? Yes.
Well, it should be 1 over a,
Oh,
right?
okay, so maybe this example, not quite as quick as my last one. I do think there's a remaining factor of a downstairs. But now when I back substitute, I said back substitute, I take that back. Now that I anti-differentiate 1 respect to theta, I get this. Now when I back substitute, I think I get this. So I'm just trying to shake you guys up. From here on out this summer session, or from here on out in your mathematical career, if ever I want to evaluate an integral, just like the second one right here, but downstairs instead of a 1, if I've got an a squared, I'm simply going to get my inverse tangent of my x over a plus c is just that unlike with the inverse sign up here, I get an extra coefficient out front, which is a reciprocal of a. Oops. Are you there? All right. If you are, let me recap what I said last time in class. I know I'm repeating myself. I'm not going to answer questions 1 and 2. We've already answered them. But let me recap globally what this approach is. If in the integrand's position, I've got an expression like an a squared minus x squared, that kind of screams out at me that maybe an appropriate substitution if a u sub doesn't work might be allowing x to be equal to a times the sine of theta. Why? Why is it the case that if I had this somewhere in the integrand's position, this might help clean up in the integrand's position? Why?
Somebody smart said that, made that up.
Somebody smart said that and made it up. No, I think you, relaxing, kicking your feet up, can say this. With this two-termed expression, replacing x with this, gives me a squared minus a squared sine squared theta. Pulling out an a squared gives me a squared open parentheses, 1 minus sine squared theta close parentheses. But now using Pythagorean identity, the very first one, that gives you a squared cosine squared of theta. It allows me to replace this two-termed expression with a one-termed expression, and a lot of times when it comes to integration, that makes your life easy. I think, however, if you had not this difference of 2 squares, but the sum of these 2 squares, using the same logic that screams out at me that maybe I should make a substitution for x, which is a times the tangent of theta, so I can yet again employ a Pythagorean identity, and rewrite this two-termed expression as a single-termed expression, namely a squared secant squared of theta. Oh, shoot, there's one more. If I have the difference of 2 squares like the first case, but reversed, then I think making this substitution, x being equal to the secant, whoops, I meant a times the secant of theta is a wonderful choice, because that gives me a squared secant squared of theta minus a squared. Ignore the a squared. That gives me secant squared of theta minus 1. But using the same Pythagorean identity I used up here, that's going to give me a tangent squared of theta times the a squared up front. Again, replace 2 terms with 1 term.
And you don't necessarily memorize that just by knowing your identities and what they
Yeah, and again, you guys, you might be sick and tired of hearing me say this, but as a mathematician, I don't memorize any of this garbage. I just look at which Pythagorean identity applies to make my life easy. Yes, sir.
So you just substitute that even though there's not the 1 over all that stuff there?
You know what? You just brought up a really good question. Can I look at your book? I'm just curious what he says, because I don't do a good job looking at your book, to be honest. Oh, thank goodness. I was kind of worried. Almost every math or calculus text I open, if you guys have your book, I'm on page 470. The author, thank goodness, doesn't say 1 over. When I was nervous, is that a lot of authors say this. If you got to screw this, screw this, screw this. That makes me nervous. But so often I don't need to have screws in there to apply these tricks. And thank goodness your author's saying that. And I don't have to have 1 after, 1 over. These could be upstairs.
So these are identities, you don't know.
I hate to say these are identities. I'd say, let's talk integrands. If in the integrand's position you have somewhere along the way this, or this, then give it a shot with these particular trig substitutions. It might clean up your integrand so beautifully that it'll be easy to integrate.
Oh, where you make the X.
Notice, you guys, how backwards these substitutions are. You're used to so far saying, oh, u equals something in terms of my variable x. These are backwards because now I'm saying my variable x is equal to something in terms of some other independent variable. Let's give it a shot with some examples. I know we've already answered the first two. Let's jump to the third one. Candidate? Which one? Sines, tangents, secants? I think secant, definitely. And so in question number 3, with this integral right here, my goodness, am I being that sloppy today? I think I'll commit myself to allowing x to be equal to, I'll be quiet. I said, I'll be quiet. Square root of 2 times secant of theta. Now pay the consequence. Very nice. And you guys, let's just commit to the substitution. I think in the numerator's position, I have nothing more than this. Is that 2 secant squared theta? I think downstairs in the numerator's position. Does that give me a root 2 tangent of theta? Oh shoot, I forgot my scale change. Another name for dx is, well, all this business. But I think that leaves me with this. Is this helping?
Can you maybe go back a couple
Yes.
steps?
Yes.
So when you got the root 2 tangent of theta in the denominator, can you show me just the steps you...
And let me come over here and plug
Okay.
this scratch paper. Because I think you're just simply focusing on this one thing, which is what I want to do. You take a peek at this business, just like the denominator.
Yeah.
I think this is the same as this.
Yeah.
Which I think is the same as this. Which I think is the same as this. Or shall I say this?
Okay.
Which, of course, is the same as this. I don't know, you tell me.
Tangent theta.
Are you guys there?
Yeah.
And you went with the,
I did commit to the secant substitution. Have you If you are, I think in the end, I'm generating this integral. What's next?
reduction formula.
What if I don't remember it? And I don't, by the way.
Pythagorean, I did.
How about in integration by parts? And using integration by parts, I guess now I have that u is equal to something, dv is equal to something. You guys listen to my choice of words. I'm going to let dv be something that's easy for me to anti-differentiate. What do you think?
Secant squared.
Yeah, I don't like it. Not quite smooth, but this is easy to anti-differentiate. And so I guess use everything else. Committing to this, paying the consequence. Yeah, that is easy, like I suggested. So I think when it comes to the integral of secant cubed theta d theta, this is nothing more than a product of my v du minus the integral of my, did I say that correctly? Is equal to my v times u minus the integral times my v du, which in this case is just secant of theta tangent square root of theta d theta. Oh, shoot.
Couldn't you just split up that secant cubed of theta into? Oh wait, no, never mind.
Yeah,
All right,
I
I
could've.
just saw that.
I just have to repeat this step next.
Yeah.
But you guys, look at that. That's just not very nice. However, employing my Pythagorean identity, well, the second Pythagorean identity, if I can write correctly, I think I have this. Well, another name for tangent squared of theta is merely secant squared of theta minus 1. Would you guys agree? But now when I split that last integral up into two other integrals, I see the secant cubed of theta d theta, well, it's an integral anyways, this first term. Minus the next integral. Plus the last integral. Do you guys see what's going on? Now when I take this beast and add it to both sides, I get two of them over here. And dividing both sides by 2, I guess that gives you that the secant cubed of theta, well, again, the integral of it, is nothing more than 1/2 times the secant of theta, tangent of theta, minus the integral, plus this integral over here, which you and I recognize as...
ln of secant of theta plus tangent of theta?
Okay, in absolute values.
Yep.
Plus 1. I meant plus c. Do you guys agree?
Why not?
Did someone say no?
I see.
Oh, this is plus, and that's multiplication. Oh, shoot, I didn't answer my question, darn it. If that's 1/2 of that, I guess in the end, I'm really just simply left with, I can't read that far, is this correct? Secant of theta, tangent of theta, plus natural log of the absolute value of secant of theta, plus tangent of theta, plus 2 times c, but that's just another c. You guys, this is so much fun. It's like doing puzzles. You don't seem to be having much fun.
You're not being graded.
Not gonna be great, yes. How about example 4? What do you think would be the appropriate choice?
Cotangent? Or no?
Yeah, don't be careful, just give me the function. I think it's gotta be a tangent because underneath the squared symbol I got a sum of 2 squares. And so I think the tangent function is the appropriate choice. You guys, am I walking too fast? I'll slow down a little bit. Taking a peek at my 4th example, I have this interval. You guys seem to agree with me that I should allow x to be something involving the tangent function. It's just that my a squared is equal to 3, so my a itself is going to be, well, root 3. And I'll pay the consequence of my actions. Now, committing to this particular substitution, I think what that leaves me with is nothing more than the integral of 1 over a bunch of stuff. Let's talk about the stuff symbol by symbol. I think another name for x squared is 3 tangent squared. I like it. I agree. You guys do the next one. What's another name for root 3 plus x squared? Root 3 secant of theta. Perfectly put. Oh no, I missed something. I forgot about my scale change. I guess my dx becomes a root 3 secant squared of theta. Now maybe there's a tad bit of cancellation with these coefficients. 1 remains downstairs. If you guys don't mind, I'll slough off and pull it out. But that leaves me with the ratio of the secant of theta to the tangent squared of theta.
Secant squared theta minus 1 sub and then split it.
You could change the
Unfortunately not. I
tangent
could have
into
split if they were
secant terms.
reversed. Change them to
Secant terms? No.
that's what he
that'll
just suggested, but it doesn't seem
Yeah.
to help.
U subs?
I just tried, I can't see anything directly.
Give up?
No, I don't wanna give up. Anybody? When things look difficult with secants and tangents, what do you wanna do?
1 minus, oh, that's what you just said then.
Convert back to your basic building blocks, which are sines and cosines. And so I think maybe rewriting this in terms of sines and cosines, that gives me a 1/3 times the integral of, actually, I really don't know. Is that a cosine over sine squared?
Now you can do U subs.
Yeah, life's a piece of cake. Now, if I allow u to be equal to the sine of theta, its derivative is directly a factor up in the upstairs integrand's position. Then committing this u sub, I think I'm basically integrating nothing more than 1 over u. Did I misspeak? I meant 1 over u squared, which is still a piece of cake. Now I'll back substitute once. And I'll back substitute another time. That's negative 1/3 times the cosecant of theta, which is I can't see it. Does anybody else see it?
You gotta
Draw a triangle. I think this particular sine for x means the tangent of theta is x over root 3. So if I embedded theta in a right triangle, to say that its tangent is x over root 3 simply means that the opposite side over the adjacent side could be represented as this ratio. It just simply means the length of the hypotenuse is the square root of 3 plus x squared. Oh, by the way, it's exactly what I had somewhere in the integrand's position initially, thank goodness. It's just a sign that I'm not committing any errors. And having said that, you guys take a peek at what I have up there. What can you say about the cosecant of theta? I asked. What can you say about the cosecant of theta? I can ask it 3 times. Root 3 plus x squared over. Yeah, we'll say with confidence.
X.
Thank you. Plus c. I agree. And I'm abiding by mathematical etiquette. I rewrote my answer in terms of the original variable.
Now is that
Yes.
all? Sorry.
Yes.
Last step, just the 3 plus x squared, where did you get that again?
I got it from here. Cosecant of any angle theta, if theta is embedded in a right triangle, could be interpreted as a ratio of the hypotenuse to the opposite side. Just using my right triangle trigonometry. So I'm just going back to my right triangle definitions. Cosecant of this angle is hypotenuse over opposite.
3 plus x squared.
My apologies, sir. That came from this. Don't look. Since I didn't have the hypotenuse, because it's a right triangle, I can generate that hypotenuse by looking at the square root of the sum of the squares of the 2 legs. Just using the Pythagorean theorem. A squared plus b squared
We got
equals
the
c squared.
root 3 and the x from.
I got that from this statement right here. If you allow me to rewrite. Doesn't it say this? But again, if theta is embedded in a right triangle, saying its tangent to this fraction means the ratio of opposite side to adjacent side relative to theta is that fraction. That's really where it comes from. David.
So you would always be able to, is that always the case, the side that's missing is going to be one of your, the x squared minus a squared and,
Can I rephrase that? It'll involve the sum or difference of 2 squares that you originally had somewhere in the integrand's position. Now, it might be a little convoluted, like maybe my next example, but it'll be somewhere.
okay. And you know you've done something right when you did that.
Yes, yes, I agree with that.
Knowing when you approach this kind of problem, do you always embed the angle when you come to that point to where you would be able to recognize that?
I would definitely. Yes. Oh, you guys, my examples they're too
Easy.
yeah. So can I raise the level of complexity? Yep. So can we take a peek? Oh, my favorite example, number 5.
3 plus sines.
What's that?
Sure you don't want to switch one of the signs?
You can
Factor it.
you can factor it.
Oh, I'm positive.
Yeah, you could definitely factor
I'm
that.
positive.
Thank you. Factors.
So do you guys think this trig substitution technique's pretty darn straightforward? Or is there a bit of work involved?
There's work involved.
I think there's a work involved, and for that reason, I probably want to apply an easier technique if I can. And you take a peek at your denominator. It's quadratic.
Mhm.
So if I were to apply u sub, its derivative would be in the numerator's position, which would be.
Why would you do the use of?
Let me rephrase it. This is
Okay.
important. If my denominator is quadratic, and I were to apply a u sub, then its numerator better be linear. And so I think in this example, you guys take a peek at my denominator. I got a 2x squared plus 3x plus 2. If I allow you to be that denominator, what would u be?
4x plus
4x plus 3. But my numerator is an x plus 1. And if I want my numerator to be the derivative of my denominator, neglecting some kind of numerical coefficient, then I think what I'm going to get upstairs is an x plus, what did you say it was? It was 4x squared.
No, just 4x plus 3.
My apologies, I misspoke. I meant 4x
Yeah.
plus 3. Yes.
Can you use your color markers?
Yes, I can. This is important. And using my color markers, David, I'm suggesting this. I maintain the derivative of this beast is a 4x plus 3. Or if I pull out a 4, I guess I mean an x plus 3/4. And you have to be impressed with this. That means if I allow you to be everything in red, its derivative, neglecting the numerical coefficient, is exactly what you see in green.
So what happened to the 4?
Oh, the 1, you're right, I messed up. Sorry, I gotta compensate. I guess I'm gonna rewrite 1 as a 3/4. I better rewrite it as a 3/4.
Plus 1/4.
Plus 1/4. Guys, think about it. I just added a funky looking form of 0. Up here, I added a negative 1/4 to bring it down to this, and added a positive 1/4 to bring it back up. I want a yes or no answer. When you look at these two Christmas colors, does it make your life easy with the use of?
Yeah.
Yeah, it really does. After all, diving in, committing to this, splitting this up into two different integrals. I think the first one is so easy to handle. After all, with that very first integral, I'm going to dive in and allow my u to be everything you see in red. And I'm going to allow what you see in green to be what you see as a derivative for u. Happy? Okay, so you got a few
So,
frowns. I guess you're not
how'd you-
terribly happy because if I'm going to differentiate in red, what should I really get?
3.
I really should get a 4x
Well, a 4x
plus 3. Okay, so I'm a little off, you guys, but you know what? I can fix it. After all, I do think if I pull out a factor 4, I'm left with this.